size, right, then you would just sort of pair them up with each other and agree not to compete for the other guy's clients, right? So the heterogeneity of the products or firms is also harmful because it makes it harder to define the optimum, right? Imagine that I'm a lemonade stand and you're a beer stand, and we're trying to collude with each other because both are sources of refreshment. Well, exactly how much beer is equivalent to how much lemonade in terms of what it's doing, and the prices are different, and how do we figure out exactly how we're going to collude, right? That's going to be much harder. And it's also going to be much harder to know exactly what a defection is, because imagine you start selling your beer and it's a bit colder, and whereas I cool mine using ice, and I put in more ice cubes. At what point is what's the translation between those? And at what point are you cheating, or are you just responding to the weather, et cetera, right? Price transparency is going to make it easier to detect defection. So if I can see what prices you're charging, it's going to be much easier for me to punish you. If I can't see your prices, if you can offer, say, secret discounts to people for buying from you, it's going to be much harder for me to track your defections, right? Industry concentration, having a small industry, as Jackson said, also helps, because there's less people I need to keep track of, just as in the externality problem, right? When there were a ton of people, it was really hard to coordinate people's behavior, to monitor everyone, to bargain, right? Whereas if there's a small number of people, that becomes much easier. If demand moves around all the time, it's going to be much harder to do this, because it's going to be easier for people to conceal what was really a defection as just being part of the natural fluctuations in demand, right? The more frequently we interact with one another, the easier it is going to be to quickly detect transactions, right? And their defections, and therefore punish them quickly. If we only interact infrequently, right, then someone could defect, but I might not be able to punish for a long time, so it would be worth it to them to defect. If demand in the industry is growing over time, that helps you. If it's falling over time, that hurts you. Why is that? Well, if it's growing over time, then you want to collude early on, right, in order to maintain the rest of the market. If it's falling over time, you're going to want to grab what you can before the market falls apart, right? And so that you can sort of imagine that as an industry grows, it might have collusion, but then as it starts to decline, it would all collapse. Okay, so all of these determine the extent of deterrence that's possible, right? Now, we said that you could deter people by shifting around the market shares, but most often the way deterrence happens is through some sort of a price war, where firms punish each other by cutting their prices, and they all do worse, but at least they deter defections, right? And so a simple way to summarize this is through what's called conjectures, which asks if one firm lowers its price, what do they expect that other firms are going to do? If they think that there might be a price war if they defect, then they'll expect other firms lower their price when they lower their price. On the other hand, if in other situations when firms say we're being very aggressive, if I lower my price, the other person might actually raise their price. Who knows, right? So you can also think about this in terms of quantity, which is rather than holding fixed everyone else's quantity, I could think that they might change their quantity when I change my quantity. If we're colluding, if I reduce my quantity, other people might reciprocate that by reducing their quantity, right? On the other hand, if we're in a model where I'm taking other firms' prices as given, then when I increase my quantity, other people are going to reduce their quantity, right, to keep the price fixed. So models and how much you expect one thing or the other, of course, depends on Stigler's factors, because that's going to determine how much collusion there is, how much you expect firms to respond. Models incorporating these features are called conjectural variation models, because there's some parameter which says how much do I expect other firms to change their behavior when I change my behavior. Okay. So notice that the Cournot model is in some sense just a version of the Bertrand model, but with conjectures, right? Because I conjecture that if I lower my price, rather than other firms keeping their prices as given, I think they're going to adjust their price downward so as to keep their quantities fixed, right? On the other hand, the Bertrand model is just the Cournot model, where I think that if I increase my quantity, everyone else will reduce their quantity by exactly as much as to keep the price fixed. OK. So therefore, the conjectural variations framework is sort of a broad framework that allows us to put collusion and all these different models together into one place. OK. So just to see how this works, let's consider the simplest Cournot model, right? So again, you have quantity times price, which is a function of my quantity and all the other firms' quantities minus cost. But now let's add an extra thing. Rather than holding fixed everybody else's quantities when I change my quantity, let's assume that firms know that the quantities of other firms will change when they increase their quantities, right? OK. So in this case, Chairman, can you tell me what the optimal pricing rule is going to be? No. Anyone else want to try? Yeah, it's real.
You're still going to want to set marginal revenue to cost.
Yeah.
So we'll use the same marginal revenue we were using before, but we'll add that term. So it'll be P plus P prime Q plus P prime Q times the extra term equals cost.
Times dq dqi. Exactly. Exactly. So that's exactly what Israel just said. It's P plus P prime times Qi times 1 plus dqi, little dq negative I, dqi is equal to cost, right? So notice that if when I increase my quantity, other people increase their quantity, so they're punishing me for producing more, right? Then that's going to raise the size of this term and create a bigger markup, right? And therefore, the marginal revenue will be further below price, and prices will rise because of the collusion, right? So this is called a conjectured accommodating reaction. It says if I'm nice, other people will be nice to me by reducing their quantities. On the other hand, if other people, and this is how we facilitate collusion, is through that sort of punishment, right? On the other hand, if when I increase my quantity, other people reduce their quantity, that's going to lead to lower prices, right? This was on last year's exam, sorry. But if how much I think, if I think everyone else reduces their quantity by exactly the amount that I increase my quantity, then this is going to be like Bertrand, right? Because the prices will be fixed when I increase my quantity. So you'll get a -1 there, and prices will be set equal to cost. So that shows us why we get prices equal to cost in Bertrand, right? We can also do this starting in terms of prices, starting from Bertrand or differentiated Nash prices. OK, so now let's return to our favorite constant elasticity example. Imagine that we have two firms again, and that I think that when I increase my quantity, the other firm will increase their quantity by 0.1 of how much I increase my quantity, right? So then what is going to be the marginal revenue expression using our example from before, King?
Well, with constant elasticity, then P equals 1 over Q.
Yeah.
So you're going to have Q. Then so I'll have like so then that times price. So
this is 1 plus 0.1, right?
right. So times. So you'll have like P over. Oh, I'm sorry. Yeah. P over P plus 1.1 P prime QI.
And P prime, remember, P was equal to 1 over Q, right? And so P prime is equal to what?
1 over Q squared.
Negative 1 over Q squared. Exactly.
Yeah.
So we get 1 over Qi plus Qj minus 1.1 times the second term that we had. And we set that equal to our cost, which is 1, right? OK, so Chairman, can you come and solve out for the quantity that firm I is going to choose as a function of the quantity firm J chooses? So the reaction function, like we had before.
So you want me to solve that thing set equal to 1?
Yeah.
I can just. And what am I solving for?
You're solving for QI.
For QI, okay. So there are a lot of QIs. So I just put all of them together.
That sounds good. I'm all for that. Nice. OK.
And then this all goes over here.
You need a negative out front of that guy, don't you?
This, oh yeah, sorry. Oops, and then this thing goes down here again. And then oh no.
You've got a quadratic formula, dude. So you just want to set that whole baby equal to 0, right? And do the quadratic formula.
What's the quadratic formula?
Can't help you with that one. Oh, you mean what is it? What is like the actual expression?
No, I mean, I don't see how it applies.
Well, but because Qi is squared, and then Qi is linear here. And so you have a square term and a linear term, right?
Oh, oh, and then.
Yeah.
I don't.
You know how to do the quadratic formula?
If there's like two squared things.
Well, here this is squared, and then you've got a linear term in front of it, and then you've got another linear term in front. You put the linear terms together, they put the square terms together, you put the constant terms together, and you do negative b plus or minus.
Oh.
QI is like your x.
Oh.
Yeah.
Oh, Qj is constant because we're assuming.
Yeah.
Yeah.
Oh.
Discriminant.
Okay. Yeah. I can. Oh, this is so complicated. So it's like x equals negative b minus square root. So here a is negative 1.
Yeah.
That's what quadratic.
B equals, okay, we factor out the Qi, so it's negative 0.1 minus 2 Qj.
Yeah.
And then C is this thing, so negative, or Qj minus Qj squared.
Okay, I'll let you leave it there. Nice job. Give them a round of applause. Good. Exactly. So you get negative qj plus 0.05. 0.05. Oh, because you divide through by 2a. Plus the square root of 2qj squared plus 1.1 qj plus 0.05 squared. So that's a little bit of a mess, but as before we can plug it into Mathematica, and you get that the quantity 1 equals quantity 2 equals 0.45, which is less than 0.5. So this helps the firms collude, right? Because remember that before, the reason why in Stackelberg the firms produced less was that they thought that, the leading guy thought that if he increased his production, the other guy would also increase his production. That got him to reduce his production. Similarly here, he thinks that if he increases his production, the other guy will increase his production to punish him, and that leads him to reduce his production, right? OK. So strategic effects are just one reason why conjectures might seem reasonable. On the other hand, anticipated strategic substitute behavior or aggressive conjectures has the opposite effect, right? And so this shows how conjectures can sort of put together a lot of the stuff that we were talking about strategic effects, about different types of conduct, and about collusion. OK, guys. Thanks. 2 more classes.